Is this organic compound a primary, secondary, or tertiary alcohol? We're supposed to give a reason for the answer. So let's go ahead and take a look. Right, so in compound A, let's just zoom in on compound A. We have 1, 2, 3, 4 carbons. So that should be butanol, right? We do have a branch here that I'm not accounting for, but we're going to take care of that. So let's take a look. Let me just circle that. This is our longest chain. We can take this as our longest chain. Even though if we go up, we would still get the longest chain of 4 carbons. Let's just take that as our longest chain. And then we have a branch on the second carbon and the functional group. Right, that is what we are dealing with. Let's go back to the question. Is it a primary, secondary, or tertiary alcohol? Well, this is a tertiary alcohol. So let me just write that down first and then explain to you why I'm saying so. This is a tertiary alcohol, right? Why do we say that it is a tertiary alcohol? It is because, take a look at these. This carbon that is bonded to OH. The carbon that is bonded to OH is bonded to 1, 2, 3 carbons, right? So if the carbon that is bonded to OH is bonded to 3 carbons, it makes it a tertiary alcohol. If it was bonded to 2 carbons, it would make it a secondary alcohol. And then if it is only bonded to 1 carbon, it would make it a primary alcohol. So right, it is a tertiary alcohol because the carbon bonded to OH is bonded to 3 other carbons. There we go. So that is 2.1.1. Let's take a look at 2.1.2. Write down the IUPAC name for the above mentioned compound. Okay, so like we have figured out, we have 4 carbons on our longest chain. So that is butane. And then which carbon is our functional group found? Well, if we start counting from the left, we have 1, 2, 3. But if we start counting from the right, we have 1, 2. So clearly we have to start numbering our carbons from the right. So we're going to have butane, 2, all. But we need to account for that branch there. We need to account for that branch. So on the second carbon, we have 2-methyl. So there we go. 2-methyl butane 2-ol. That is the IUPAC name of our compound A. 2.1.3. 2.1.3. The above mentioned compound undergoes an elimination reaction. Write down the structural formula of the product that is formed. Elimination reaction. So let me just write that structural formula without condensing it. So this is OH, and then hydrogen. We need another. Okay, here we have a branch, so let's put that there. And then elsewhere we have hydrogens. Okay, so which elimination reaction can an alcohol go through? Because this is an alcohol that you're dealing with, right? So the elimination that an alcohol can go through is dehydration. It is dehydration. The alcohol loses 1 hydrogen and an OH, right, making it H2O, as dehydration. That is the only elimination reaction alcohols can undergo through, right? So it means that the structural formula of the major product formed should be an alkene, right? This question is very specific. Major product, right? We have a major product and a minor product for these reaction. We have a major, well, for the product of an elimination reaction of alcohol, right? Dehydration. We have a major product and a minor product. So this is just the alcohol. This is not the answer. This is not the answer. This is just the alcohol. We just draw in the structure of the alcohol so that we can better make sense of it. So the major product of dehydration that compound A will undergo will look like the following. So we have 1, 2, double bond, carbon, carbon. So there we go. And then hydrogen everywhere else. Hydrogen everywhere else. So 4 bonds on that carbon, it is satisfied, and let's just fill out hydrogens everywhere. So let's check the number of bonds. This 1, 2, 3, 4. So everything is fine. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, right. You have to calculate the number of bonds to avoid making any mistake. We also need our branch. I'm forgetting to put the branch here. Because we have a branch here on the second carbon. So we don't have a hydrogen here, but rather we have a branch. So that is what we have. That is what we are dealing with. Let's check if the number of carbons is still intact. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I'm happy with that. Right, let's move to the question that follows. 2.2, 2.2.1. Consider the organic compound B. 2.2.1. Define the term functional isomer. Okay, so compound B is pentane 3-on, so that is a ketone. But well, the question wants us to define the term functional isomer, so let's go ahead and do that. Functional isomer, organic compounds with the same molecular formula but different functional groups. Same molecular formula but different functional group. That is a functional isomer. And then 2.2.2, I'm expecting that the question is going to have something to do with isomers. Write down the homologous series to which the above mentioned compound belongs. Okay, compound B. This is 2.2, and 2.2.2 is a sub-question of 2.2.2. Okay, I was starting to ask myself which above mentioned compound, because I was thinking 2.2.1, but it is compound B that we are referring to. So compound B is a ketone, but the name of the homologous series is actually not ketone. It is ketones. It is in plural, by the way. Yeah, it's one of those things that we usually overlook. But the name of the homologous series is not ketone. It is ketones. Yeah, if you go to your exam guidelines, that is exactly what you're going to find. You're not going to find the homologous series ketone. No, the homologous series is ketones. Right? We just been, more precise. We live in no stone unturned. Okay, that is 2.2.2. Let's do 2.2.3. IUPAC name of its functional isomer. So the functional isomer of ketones is aldehydes, right? The functional isomer of ketone is aldehydes, right? They have the same, a aldehyde looks very similar to a ketone, but the only difference is that the double bond oxygen is at the end. So here we have pentane 3-on. So the ketone that you're looking for is pentanol. That is, the aldehyde, not the ketone I meant. The aldehyde that we're looking for is pentanol. Pentanol and pentane 3-on are functional isomers. So what are we looking for? IUPAC name of its functional isomer. Oh, okay, we're done then. We're looking for the IUPAC name. I thought we were looking for the structure, right? But we're just looking for the IUPAC name. The IUPAC name is pentanol, right? 2.2.3. What about 2.2.4? Letter that represents its positional isomer. So we are dealing with pentane 3-on, right? So the positional isomer is pentane 2-on. It has only one positional isomer, right? Because we have 1, 2, 3, 4, 5 double bond oxygen, right? If you put this oxygen here, it is pentane 2-on. Same is true with when you put it here, you'll still have pentane 2-on, because we have to start numbering from the side closest to the functional group. So we're looking for pentane on here on our table. Letter that represents is positional isomer. Okay, let's take a look. Pentane looks to be compound E. It looks to be compound E. Because take a look at compound E. We have 1, 2, 3, 4, 5. So that is where our pent is coming from. And then on the second carbon, double bond oxygen. So there we go, pentane. That is compound E. So the letter that represents is positional isomer. The answer is E there. The answer is E. It is compound E. Pentane. Write down the balanced equation using molecular formula for the complete combustion of compound F. So let's take a look at compound F. Compound F is 1, 2, well, not 2 anymore, but actually 3, right? So we have 5 carbons in total. We have 5 carbons in total. So that is C5. How many hydrogens do we have in total? We have these 3 here. We have these, which gives us 6. And we have 3. So that is 12, right? So H12. And then it is a combustion reaction. So it is excess oxygen to give us CO2 plus H2O. We just need to balance this equation. So C5, C1. What do? We put 5. In putting 5, the carbons are balanced. And then we move to the hydrogen. H12, H2. So we put 6. We put 6 in attempt to balance the equation. And now take a look at this. We have O2 here. And here we have 5 multiplied by O2, which is 10, plus 6 multiplied by O2, which is 6. So this is 16. And then in order to get 16 on the left-hand side, we must multiply with 8. So there we go. We have our balanced combustion reaction. Here we go.